Hi guys. Today we are going to see some left out things like Turing machine language and how to represent Turing machine using transition diagram. Right? It is a very short video. So the language accepted by a Turing machine is known as recursively enumerable languages. So already we have seen two automatons. What are they? Finite automaton, that is DFA and NFA, followed by PDA. Then finally we are now seeing a Turing machine. The language accepted by a finite automata is known as regular language. The language accepted by the PDA is known as context-free language. Now, the language accepted by a Turing machine is known as recursively enumerable language. Here in Turing machine itself, we will see two variations. One is recursive and another one is recursively enumerable language. We will talk about all those things in fifth unit. Only two or three topics are remaining in this unit. So, while going into fifth unit, we'll see something about the recursive and recursively enumerable languages. So, time being, the language accepted by a Turing machine is known as recursively enumerable languages. Why? The name is different, right? There we called that is we called the language accepted by finite automaton as a regular language. Why? Because the grammar used for representing that is regular grammar. So we named that language as regular language. Similarly, in PDA, the language used for recognizing the languages of PDA or context-free grammar. So we call that language as context-free language. But here the language is different. The grammar used for representing the languages of Turing machine is unrestricted grammar. But the name given for the language is recursively enumerable languages. There is a reason behind this naming convention. Recursive means repeatedly doing something. What it repeatedly do? Enumerable means listing out. So it repeatedly lists out the strings accepted by the given mathematical model. So we call that as recursively enumerable language. It means that it will say yes to only to the strings that is accepted by it. When I pass any string that is not accepted by this machine, it will not say anything. It will be in recursive state. So that may be the reason. So the researchers find these two reasons for this naming conventions. So just we'll stick whichever is convenient for us. But no one is going to ask us why they have given this name. But anyhow, we'll know the reason behind this naming convention. Okay, fine. Now we know the name for the language accepted by the Turing machine. Now we know that language is nothing but a collection of strings, right? So strings is nothing but a collection of symbols. I say that a string belongs to a language of a particular mathematical model when the following condition gets satisfied. What is the condition? So given a string, I'll start my move or a transition from the starting state. I'll make some sequence of transition until I reach the accepting state. That when I reach an accepting state, or when I have processed all my input symbols, and finally if I land up in an accepting state, I say that that string can be included as a language of that particular mathematical model. This rule is common for all the mathematical model that we have seen. That is finite automaton, PDA and Turing machine. Right, here also the same rule. So given a Turing machine and an input string, we start from the starting state of the Turing machine. We make sequence of transition. After processing all the input symbols, if the transition lands up in an accepting state, then we say that the string belongs to the language of the given Turing machine. So this is the reason why we write transition function only for the correct states. We need not worry about all the wrong states. Why? Because when I find an input symbol that is different from the language accepted by the particular mathematical model, automatically it lands up in a non-accepting state. So when I can accept a string only if it is landing up in an accepting state. So that's the thing. So this is just an informal definition. This is given just for an understanding purpose. This is the formal definition taken from our textbook. So let M is equal to Q, that 7 components, be a Turing machine. Then language of M. Why M here? Because the name given for this Turing machine is M. Is the set of strings W in sigma star. such that sigma star means set of strings, right? Such that here from the 7 component definitions, I infer that Q naught is the starting state and W is the input string given for me. This symbol represent a move. So star here means 0 or more moves. I do not know how many number of moves I make, but I make some moves, and finally if I have this configuration where alpha, beta are some step strings, it may be blank or it may be some symbol. For example, when I perform addition and subtraction operation, the output remains in the input tape itself, and for something else the entire tape may be blank. So I do not know, and the alpha and beta can be of any symbol, but what is an important condition? P must be in an accepting state, that is F, right? I think you are able to follow this. I am repeating again. Let M be a Turing machine. Then I say the language of M is a set of string W. We are taking in general. Sigma star, sigma is nothing but a set of input symbol. So W should be made up of the input symbols. So star means any number of symbols, any instance of the input symbols. Such that I'll start from the starting state, which is the starting state from the 7 component Q naught. What is my input string W? I make move. So this symbol represents the move. How many number of moves I make? 0 or more moves. Why they have given star? Because I could not determine the number of moves exactly. So if it lands up in a configuration like this, what does mean? Alpha and beta, they say that at any tape strings, it can be of input symbols or it can be of blank. But what is the important condition? P is some state in F. Why some state? Because F is a set of accepting states. So it can be of all the states in F or it can be of any one of the states present in F. So this is the formal definition of the language accepted by the Turing machine. And the name given for the language of the Turing machine is recursively enumerable language, right? This can be asked as a 1 mark question. Now, the last one. So, we know that all the mathematical models can be represented in 2 forms. One is transition table and another one is transition diagram. I have already introduced the transition table for you. Now, we'll see how to represent a Turing machine using transition diagram. So like the previous 2 models, any one of the representation can be used. Whichever is convenient for you, you can follow that. Either you can construct a Turing machine using transition table or with transition diagram, right? So for example, we'll take one or I'm not going to describe all the transition functions given here. Just we'll take one or two. Say here Q naught, when it scans 0, it goes to the state Q1 and replaces 0 by X and the tape head moves towards right. So how they've represented for each state? A circle or a vertex. So Q naught, Q1. So since this is a starting state, arrow mark represents the start. So here, what symbol? So this transition from Q naught, I move to Q1 when I scan the input symbol. So 0 input symbol is replaced with X. So whatever they have written here, X, and the tape head moves towards right. Similarly, we'll take one more transition. So Q1 to Q1. So Q1, when it scans 0, it remains in the same state. It replaces 0 by 0 and the tape head moves towards right. So Q1 to Q1, 0 to 0, it moves towards right. So like this, you can represent. So the remaining notation, transition and all same. The one additional information here is the direction. You have to represent the left and the right direction. You should not miss. Always you have to mention whether the table is moving either left or right. It may be useless move too, but I have to mention whether it is moving left or right. So with this we have seen we have gone through the basic thing. So in Turing machine introduction, you have to see the following thing. You must know the definition of it, then the language of it, move, then instantaneous description. Then what else we have seen? These are all some important 2 mark question which is repeatedly asked. This is general one, right? You can give the solution either here or in this form or in transition diagram notations. So now we'll move to the next topic, which is nothing but a programming techniques of a Turing machine. So this is very, very important. So from 4th unit, there are repeatedly asked 3 questions. One is the construction of a Turing machine. They'll give you any language and they'll ask you to construct it. Mostly what are all the languages that you are seeing in the lecture that will be asked. The second one is this programming techniques of a Turing machine. Either they'll this ask this as such as a 15-mark question, or they'll ask us to describe any one of these component as an 8-mark question. And the third one is the types of Turing machine, which is in the next topic. With that, this unit gets over, right? So in the next lecture, you're going to see in detail about the programming techniques of a Turing machine. What does it mean? What, am I going to program a Turing machine? No, I'm not going to program a Turing machine. But initially, while saying the introduction for a Turing machine, I say that Turing machine is as powerful as that of a computer. But computer have parallel processing, uh, parallel distributed processing, memory, there is no restriction. But here I have only one tape that is of infinite size. I'm using that tape for both input and output, storage of input and output. So how far? What are the additional features available for me so that I can perform my operation efficiently? So that we are going to discuss under programming techniques for a Turing machine. So under this, we are going to see three important things. So even they'll ask sometimes is this as a 2-mark question. So storage infinite control or a state, multiple tracks and subroutines. So in the forthcoming lecture, you are going to see in detail about all these one. Okay, with this I'm stopping. And one more important announcement is that you will be having a quiz either on Monday or Tuesday, right? So either Monday or Tuesday, just I'll inform you previously, but you keep on preparing it, PDA and Turing machine. So till this topic you just prepare for a quiz. The maximum question will be of 20 questions, and each question will be carrying 1 marks, right? Thank you.